Okay, so hi guys, so there is a little correction from the previous lecture wherein we saw the example of copper 29 with the 4s2 3d9 configuration and 4s1 3d10 configuration. So the correction is the pairing energy here is also 5, because if you can see that 3d and 3d10, by chance I got it wrong, I misjudged it, so pardon me for that. So pairing energy for here would be number of paired electrons, which would be again 1 2 3 4 and 5. So pairing energy would still be 5. So now what we do, we have the total energy in case of 4s2 39 as again minus 25e plus 5p, and total energy here is again minus 25e plus 5p. So how do we compare? Hence in these cases, when we have the same aggregated value for the total energy, so the stability of the electronic configuration is decided by the second factor, which is symmetrical distribution, okay, or equal distribution of charge or electron density along x, y and z direction. So in this case, as you can see that it is more symmetrical than this, hence this would be more stable. Okay, so just write it again over here, that if we have same aggregated value of exchange energy and pairing energy, then the stability is decided by symmetrical distribution of electron density. Okay, so hence it is clear that both first and second configuration in the previous case had equal value of total energy, which is exchange energy plus pairing energy. However, in the second configuration, electron density in 3d10 configuration was more symmetrically distributed in x, y and z direction, hence it is more stable than 1. Okay, so let's make a note on the same, that as electron density in 3d10 configuration is more symmetrically distributed in x, y and z directions, hence it is more stable than 3d9 configuration, 3d9 and 4s1. So I'm just writing 3d9 here. So okay, so it doesn't matter, 4s1, 4s2 and 3d9 configuration. Okay, so now let's take a look at spin multiplicity, which is nothing but is 2 mod of s plus 1. Let's see now spin multiplicity, which is nothing but 2 mod of s plus 1. Okay, so where s is the spin quantum number. Okay, and let's say we have also a term which is multiplicity, I think I got it wrong here, multiplicity, which can be defined as n by 2, where n is the number of unpaired electrons. Okay, So next we will be seeing some question in which you have to find out the spin multiplicity of the following compounds. Find spin multiplicity of following compounds. So first we have, what is the spin multiplicity here? Spin multiplicity would be so this is plus half minus half, which cancels each other out, so only remaining is plus half. Plus half or minus half doesn't matter here, so let's take plus half for this one. So spin multiplicity here would be 2. Let's take another example. Okay, so here what would be the spin multiplicity? So spin multiplicity here would be again 2 mod of plus half minus half 0, and plus half is remaining here, plus 1, that would be 2. Third would be this case. So spin multiplicity here is plus half plus half plus half would be plus 3 by 2 plus 1, that would be 4. Okay, so now in fourth example, let's have this case wherein we have spin configuration something like this. So here spin multiplicity would be plus half minus half 0, plus half minus half 0, only plus half is remaining, plus 1, that would give us answer as 2 rather, not 3. Okay, so answer would be 2 here. Again, let's see another example. We have something like this. So here the spin multiplicity would be 1 2 3 4 5, 2 into plus 5 by 2 plus 1, that would give us spin multiplicity of 6. Okay, so let's move on to seeing next example. So suppose for 3d9 and 4s2 configuration, what would be the spin multiplicity? If we draw the structure, first we will be seeing something like this: 3d9, this is 4s2, this is 3d9, 1 2 3 4 5 6 7 8 9. So here total number of spin would be only plus half for this one, rest all would be cancelled by each other, so spin multiplicity would be 2. And if we see the same for 3d10 and 4s1, we would have something like 4s1 here and 3d10 here. Again, the spin multiplicity in this case would be again determined by this plus half, the rest would be cancelling each other out. So spin multiplicity, this is the only spin, so this is summation of spin rather, and spin multiplicity would be 2 summation of spin plus 1, that would again give us 2. Okay, so in spin multiplicity in both the case would be equal. Okay, so we are also seeing the fact that more the spin multiplicity, more will be the stability, but in this case both the stability would be same. So had it been the case of copper, wherein we actually see both the configurations, again the stability would be higher of this one. Why? Because this is more symmetrical, having more symmetrical electron density. So we can replace it by smaller e. Capital E we are using for energy, so symmetrical electron density. Okay, let's take another example wherein we have chromium 24. One of the configurations can be 3d4 and 4s2. Okay, and another configuration could be uh, when we are half filling the d orbital, 4s1 and 3d5. So in this case, spin multiplicity would be again 4s2. Let's draw the orbitals first, 4s2 and 3d4, and here 4s1 and 3d5. For 4s2 it would be something like this, and for 3d4 1 2 3 and 4. For 4s1 it would be 1 here, and for 3d5 we would be having 1 2 3 4 and 5. So spin multiplicity in this case would be, summation of spin would be 2 half into 4 times. So 2 into summation of spin multiplicity would be, that is 2. So I'm directly replacing here. So that would be 5 here, and spin multiplicity in this case would be 1 2 3 4 5 6 are there. So summation of spin would be 3. So 2 into 3 plus 1, that would be 7. As this is having more spin multiplicity, this would be the stability order as well. Stability order or spin multiplicity order. Okay. So now let's see